Hi. Today we continue discussing kinematics, and you already know that physics is the basis for all natural and engineering and technical sciences, because physics studies the fundamental laws of nature. Also, you know the main laws of kinematics, the definition of velocity and acceleration. So you remember that the velocity, or a speed if it's not a vector, is defined as the displacement of a material point divided by the time interval during which this displacement took place. From this point, from this formula, it's obvious that the displacement traveled by a body equals velocity by time interval. This is the simplest formula in kinematics and probably in all of physics, and I would like to consider some problems related to this formula, and you will see that even the simplest formula sometimes involves complicated problems which cannot be solved just in a few seconds, and you must think about these problems, about the statement, and you must, in order to solve the problem, you must draw a sketch of what is going on. So I would like to consider problem number 12 from the collection of problems in physics by Bukovtsev. This collection of physics is recommended to you as the main source of problems for home assignment, for homework. By the way, I sent you today a message explaining the procedure for homework submission. You will submit your homework distantly using photos of your solutions, which should be sent to me by email once a week by the end of Sunday. This is the deadline. You can certainly choose a different time for sending your homework. You can send your homework on Saturday anytime, on Friday anytime convenient for you, but the end of Sunday is the deadline for the problems considered during the week. And so you should send me the solutions of problems assigned for the first week before Sunday next week, that is before October 17. Well, now let's consider problem number 12. A motor ship traveling upstream meets a raft floating downstream. 45 minutes later, so we have first time interval 45 minutes. 45 minutes later, the ship stops at a landing stage for 1 hour. That is an hour time interval, 1 hour. Then the ship travels downstream and overtakes the raft in 1 hour. Again, another time interval is given in this problem. Another time interval during which the ship travels downstream and overtakes the rafts. The speed of the ship relative to the water is constant and equal to 10 kilometers. The speed of the ship is 10 kilometers per hour. Determine the river current velocity Let's denote the river current velocity by u, and we have to find this quantity. Considering it constant, consider both graphical and analytical methods of solution. So we assume that the river current velocity is constant. It doesn't change along the river. Well, the first step in solving any problem in physics, and not only in physics, in any technical science, the first step is always the same. In order to solve the problem, you must first understand the statement of the problem. In order to understand the statement, it's very useful to draw a sketch showing all the processes considered in this problem. So what is considered in this problem? First of all, we have a river. Let's somehow draw, let it be a straight river, as if we look at it from above. And then there is a raft on the river, a raft that goes downstream. Let's assume that the river flows to the right along this x-axis. So this raft goes downstream together with water, together with the stream, with the velocity of the river flow. And the velocity is denoted by u. So this is the velocity of the river flow and the velocity of the raft at the same time. Another thing in this problem is a motor ship that travels upstream. So there is a motor ship which travels upstream, and the velocity of this motor ship with respect to water is given. This is not the velocity with respect to the earth, not the velocity with respect to the river banks, but the velocity of the motor ship with respect to the water surface. The speed of the ship relative to the water is constant and equal 10 kilometers per hour. That's it. That's what happens in this problem. There is the river and the raft floating down the river stream, and the motor ship or motorboat which goes up the stream, and then the motorboat stops somewhere and is at still during 1 hour. And then the motorboat will start from here downstream, and it will overtake the raft at some other point in 1 hour of its journey. So, in order to solve this problem, we must visualize all the processes that take place here. Suppose this is the point where the motorboat first met the raft. At this point, after the raft and motorboat met at this point, the motorboat went up the stream and it took the motorboat 45 minutes, that is time interval t1. During this time interval, the raft went downstream to some unknown point. And then, while the motorboat was standing here without any motion, the raft during this time went downstream, and it took time interval t2, 1 hour, for the raft to go down, while the motorboat was standing here. And then the motorboat started downstream and overtook the raft at some position here. And it took the raft to go to this point during time interval t3. And at this point, the raft was overtaken by the motorboat, so they met again here at this point. And we can say that, yes, as far as the motorboat is concerned, first it went to this point of landing stage, and then it standed here, it was at rest here for 1 hour, and then it took 1 hour for the motorboat to chase the raft and to overtake it. And that, for the motorboat, it took time interval t3 for the motorboat to go from the landing stage to overtake the raft. So that's what happened here with the raft and the motorboat. Okay. Now let's use the formulas of kinematics. That is this simplest formula, which applies to a uniform motion, that is, to the motion with constant speed, which is the case in this problem. So what was the distance traveled by the raft during all these time intervals? The raft was going down with the velocity, with the speed of the river flow u. And so the raft went down from point A to point B, and the distance d from point A to point B can easily be calculated because we know the total time of motion and the velocity or the speed of the river flow. So the distance can be calculated as the speed multiplied by the total time that was necessary for the raft to go from point A to point B. That's problem number 12 from Buchovtsev. So the distance traveled by the raft is given by this simple formula: the speed of the raft, which coincides with the speed of the river flow, multiplied by the total time interval, which was necessary to go from point A to point B. What happened to the motorboat while the raft was floating downstream? First, the motorboat went from point A to, well, say point P. And that was the distance, some distance, well, let it be d1, that was traveled by motorboat. And this distance d1 can be calculated as the time interval t1 multiplied by the speed of the motorboat. And as the motorboat was going from point A to point P against the river flow velocity, therefore the speed of the motorboat with respect to the ground, with respect to the river bank, was equal to the speed of the motorboat minus the speed of the river flow, of the river stream. The speed of the motorboat minus the speed of the stream of water in the river. That is because the motorboat went against the direction of river flow. And then from point P to point B, the motorboat went during time interval t3. and covered this distance, which is equal, by the way, to d1 plus the distance from point A to point B, and this is d, capital DAB. The total distance from point P to point B is the sum of two distances, PA plus distance AB. Distance AB is already written here. It can be expressed using this velocity of a river stream. And distance d1 is also written here. But we can, anyway, express this total distance traveled by the motorboat downstream using the time interval t3, during which the motorboat was traveling from point P to point B, multiplied by the motorboat velocity, or motorboat speed, which was certainly the speed of motorboat relative the water surface plus the speed of the river flow, because in this particular case the motorboat went downstream, and so the two velocities must be added together. The velocity of the river stream, the velocity of water flow in the river, plus the velocity of the motorboat relative to the water surface. So we have taken into account all the processes that took place in this problem. We have expressed distance AB traveled by the raft. We have expressed distance d1 traveled by the motorboat against the river stream, upstream, and we have expressed the distance traveled by the motorboat down the river stream with different velocities. The last two processes took place with different velocities. So this system of equations takes into account everything which happens in this problem. And the only thing remaining is to solve this system of equations. How can it be solved? Well, we can use this expression for d1 and substitute it here, and we can use this expression for dAB and substitute it here, and then we will obtain some expression, some equation, which hopefully will produce the result. And what is the purpose of our solution? The purpose is to find the velocity of river stream, the velocity of river flow, this unknown quantity u. Okay, let's do it. So first of all, d1 equals t1 v minus u plus capital D, that will be unknown velocity u, t1 plus t2 plus t3, equal to this expression, t3 v plus u. From here we must find this unknown quantity u here and here and here. In order to find it, we have to make some algebraic transformations in this equation. Let's do it. So it will be u t1 plus t2 plus t3 taken from this round bracket, and then minus t1 taken from here, and then minus t3 taken from here. So we have taken into account all the terms containing this unknown velocity u, all the terms containing u. And all this is equal to what? The remaining terms v times t3 minus v times t1. Now the solution is obvious. Unknown quantity u from here equals what? T1 and T1 will cancel, T3 and T3 will cancel. So what remains is v T3 minus T1 divided by T2. V is the given velocity of the motorboat with respect to the water surface. And T1 and T3, T2 are the given quantities, given time intervals. So we can easily calculate what will be here. That is 10 kilometers per hour, which is V. T3 minus T1 is 15 minutes, 1 hour, 1 hour minus 45 minutes. That is 15 divided by T2, which is 1 hour, and 1 hour is 60 minutes. It's convenient to have minutes both in the numerator and denominator of this fraction, so that minutes will be easily cancelled, and 15 divided by 60 will be 1 over 4, and so the answer will be 10 divided by 4 kilometers per hour, which is certainly 2.5 kilometers per hour. Such is the analytical solution to this problem. And I remind you that this is problem number 12 from Buchovtsev. If I'm not mistaken, this problem is not included in your homework. But anyway, other problems which you have to solve in your homework are very similar, because all the problems are on kinematics of uniform motion use this basic equation, which connects the distance traveled by a material point, its velocity, and the time interval. The simplest formula in physics. Any questions? Now I would like to consider a different topic related to vectors. You know what is vector? Is such a quantity which has both magnitude and direction. Displacement of a material point is surely a vector, because if a material point was here at point A in space, and then the material point was displaced somewhere to another point B, then the displacement will have both magnitude, that is the length or the distance traveled by the material point, and the direction from point A to point B. So the displacement is a vector. Should the material point go to a different direction, like to B prime, then that would be a different vector which may have different direction and different magnitude. So the displacement is a vector. Therefore, if the displacement delta x is a vector, then the velocity of material point should necessarily be a vector. In general case, these are vector quantities. And I would like to consider a problem which deals with vectors, with velocities as vectors. Problem number 9. A bus is running along a highway at a speed of v1 16 meters per second. The speed is given in meters per second. Okay, no problem. A man is at a distance of a meters, 60 meters from the highway, and at the same time he is at the distance b, which is 400 meters from the bus. So I told you in the very beginning that the first step in solution of any problem is to clarify the statement. The first step is to understand the statement, and in order the statement of the problem. And in order to understand the statement, it's very often useful to draw a sketch to show on some figure, on some picture, what's going on in this problem. So in this problem we have a highway. Again, suppose that you look at this highway from above, from the sky, from helicopter. You look at this highway, and there is a bus which runs at a given velocity v1 along the highway. And there is a man somewhere, not close to the highway, but he is 60 meters away from the highway. He is at a distance a from the highway. Somewhere in the field there is a man. And his purpose is to catch the bus. In order to catch the bus, he must run somewhere to the highway and do it in such a direction and at such a velocity as to be just in time to catch the bus. That's the purpose of this man, is to catch the bus. And at the beginning, the man is at distance b from the bus. So this is distance b. And the question in this problem is, in what direction should the man run to reach any point of the highway at the same time as the bus or before it? The man can run at a speed of v2, which is given as 4 meters per second. In what direction should the man run in order to catch the bus? That's the simple sketch which demonstrates or illustrates all the processes which take place in this problem. The bus running along the highway, and the man and his position in the field away from this road, and the man wants to run somewhere at a speed of 4 meters per second. That is probably the maximum speed with which this man can run. So if he runs in this direction, will he ever catch the bus? No. If he runs at this direction, will he ever catch the bus? No. So we must find such directions. Probably this one, I don't know. Probably this one. But we must find such directions which are good for this man to catch the bus if he can run at a given velocity. The easiest way to solve this problem is to change the frame of reference. Now we are somehow associated with the ground, with this man who is standing in the field. And we are also supposed to associate ourselves with the ground. And the frame of reference from which we observe all the processes here is associated with the ground. But it's also useful to think about what will the passenger of this bus observe. The passenger sitting in this bus, he will observe something different, because the bus is moving with respect to the ground, but the bus is not moving with respect to the passenger. The passenger is inside, and the bus is at rest with respect to the passenger. So if we imagine that we are in this bus and we are passengers and we are looking at what is going on around, we will see the bus at rest, because now we are in another reference frame related to this bus or connected to the bus, the reference frame of the bus. In this reference frame, the bus has zero velocity. But the ground and the highway, this road and everything is moving in the opposite direction opposite to the direction of the bus motion. So if the bus is moving from left to right, then the ground and the highway moves in the opposite direction, including the man, including this man. He is standing in the field and he moves at this velocity. That is the velocity of the bus v1. If the man is at rest, standing here, then he is moving together with the ground with respect to the bus with this velocity. And now, for any passenger inside this bus, it's obvious that the man, in order to catch the bus, should run along this line, along this straight line, or probably along some other straight line which has this direction, in order to catch the bus, in order to reach the highway together with the bus at this point or before the bus. So, what is velocity? Velocity is the displacement of material point divided by time interval. So if we choose the unit time interval, like 1 second, then the velocity will numerically coincide with the displacement. So v1 is the displacement of this point of displacement of man during 1 second. And if the man runs at some direction, then there will be another displacement of the man if he runs in the field. For example, if the man runs in this direction with velocity v2, then the resultant displacement will be from this point A to this point, which is the end of vector v2. The man can run in any direction. So I can draw a circle with radius v2, and this circumference will show the possible positions of the end of this vector. In whatever direction the man runs, the end of vector v2 will belong to this circle. So any possible displacement of man will consist of displacement to the center of this circle and then to the displacement to the circumference, to some point on the circumference. In order to catch the bus, the man should run either at this direction in order to be on this line connecting point A and the bus is at standstill here, is at rest, because we are in the reference frame related to the bus. The bus is at rest, and everything, all other subjects move here, the field, the road, the man, everything is moving, but the bus is at rest. So the man will move in such a way that the displacement of the man consists of two parts. First, the displacement due to the motion of the field and the road, and then the displacement due to the velocity of the man running in the field. So if the man runs here, he will catch the bus. Also, if he runs here, he will catch the bus. Also, if he runs here, he will reach the highway before the bus. And also, if he runs here, he will reach the bus, because he will be on the same line. But if the man runs in any other direction, he will miss the bus. So the possible directions are here. That is the geometrical place of all possible directions along which the man can run in order to catch the bus, from this point to this point. So if we know everything here, distance A, which is given, distance B, also given from the man to the bus at the very initial moment, and then we know this velocity v1 and velocity v2, we can draw this picture according to the magnitude of these vectors. And then we can solve this problem geometrically. Just drawing these angles and drawing these vectors and showing that the man should run in any direction which belongs to this angle. The man should run in any direction. In order to get the bus, yes, he can choose any direction. It will take different time to catch the bus, but anyway, finally he will catch the bus if he runs somewhere in these directions. Okay, we have 5 minutes interval. Okay, so we continue after this short interval, and it's easy to see that any passenger in this bus will conclude that if the man moves along this line, he will surely catch the bus, but also if the man moves along some line to get to the road before the bus, he will also catch the bus. So any angle inside this interval is possible. There is another question to this problem. At what minimum speed should the man run to be able to meet the bus, and in what direction? At what minimum speed should the man run? Okay. So in the second question, the speed of the man running is not given. We have to find the minimum possible velocity and its magnitude and direction in the second part of this question. Okay, so if the man chooses to change the direction along which he's running, he may choose the direction perpendicular to this line AO, for example. The line AO connects the initial position of the man and the bus. If the man runs along perpendicular to this line, then the length of this vector will be minimum possible magnitude of velocity, which is necessary to catch the bus. In order to find it, in order to calculate it, I will draw this picture again, no problem. So this is B, and this is A, and this is point capital A, and this is vector V1. So if the bus velocity is vector V1, then this is actually minus V1, because this velocity has opposite direction. But we don't need it. The minus only shows the direction, which is clear anyway. So we will need only the magnitude of this vector in our calculations. And now we see that in order to catch the bus running at a minimum possible velocity, the man should run in this direction, and then his velocity v2 will be minimum possible. Because if he changes the direction, for example, if he chooses to run along this direction, the velocity will be much, much larger. And the perpendicular will give you the minimum possible velocity. So it's obvious that this angle alpha equals this angle alpha, and therefore we can write that v2 divided by v1, I mean the magnitude of the vector, just the length of this vector. This is just a number. This is not a vector here. This is the magnitude of the vector. So v2 divided by v1 will be a sine of this angle alpha, opposite leg in a right-angled triangle. This is a sine alpha. And sine alpha can also be expressed as A, side A divided by this section B. And from here we can immediately find the minimum velocity v2, the minimum velocity of the man, and it will be v1 A divided by B. And if v1 is 16 meters per second, and A is 60 and b is 400, then it's easy to calculate everything. We can divide by 4. It will be 10, and 4 we can divide by 8. Then that will give you 2, and that will give you 5. So that will be 2 times 6, 12, divided by 5. That will be 2.4 meters per second, something like that. (2.4 meters per second). That will be the minimum possible velocity. And if the man runs at this velocity using this direction, then he is sure to catch the bus. But if he chooses to run at a smaller velocity, he will miss the bus. This is minimum possible velocity to catch the bus. Now a few words about the notations. In Russia, we are used to indicate a decimal point as a comma, 2.4. That is in Russia. In the United States, they will put it like 2.4. That is in US. 2.4. In the United States, if you have a large number like 34,123.5, they often use comma in the United States to separate 3 digits, and then another 3 digits, and then another 3 digits. In the US, they often use comma. That is the notation which is adopted in the United States and in most of the scientific literature in the world. In the Russian language, we use different notation. Instead of comma, the comma in Russia is used as a decimal point. So the comma and the decimal point is the same. But in order to separate 3 figures, we use just a space, just a small interval, just a space. So in Russia, we will draw this figure like this: 34, small space, 1, 2, 3, comma 5. So that's in Russian. Sometimes they don't even put this space here. Sometimes we put large numbers without any space, believing that the reader is smart enough to understand that the space should be here and the space should be here. Okay. So sometimes the space is used and sometimes no spaces are used here to separate 3 digits in large numbers. So this is some difference in notations as far as decimal points are concerned. In the last problem, we have considered 2 different ways of solution. First, a geometrical solution without any calculations, just using the figure. And second, analytical solution, when we used formulas and obtained the final figure. Many problems in kinematics can be solved using 2 different ways, both analytical and geometrical. So I will refer again to problem number 12 to demonstrate a geometrical solution of problem number 12.
So just using, like you do not have to state the direction, just by drawing the teacher will know the direction.
Well, you will know the direction if you draw a sketch, if you draw it correctly to indicate what is, to show what is going on, then you will know the direction. You will see it. You can show the direction geometrically. You can construct the direction on your sketch. That's quite possible. And that may be the first step in solution. First step, draw a sketch, find the direction geometrically, and then the second step, use formulas to calculate.
Yes. And the speed that we're given that the man can run at, the 4 meters per second. So what does it serve us?
Sorry, what?
The speed that we were given, the 4 meters per second, the speed that the man can run. Yes, what did it serve us?
What did it say?
What did it help us? Because we did not use it, we just found another speed. Like
We know both the speed and the direction. We have shown the direction.
yes, but
It's
we're
perpendicular to line AO, right?
given- yes.
So we know the direction and we know the magnitude. It means that we know everything about the velocity of the
We're
man.
given the speed, the man can run, the 4 meters per second. Do you remember it?
Yes, initially the speed was given as 4 meters per second. But in the second part of the problem, in the second question, it said, find the minimum possible speed with which the man should run in order to catch the bus. So the first part of the problem involved this given speed of 4 meters per second. But the second part of the same problem had different question. Find the speed of the man, the minimum possible speed. So it differs from 4 meters per second. It turned out to be 2.4, right? Okay. So I return to problem number 12 in order to demonstrate a graphical solution. A motor ship traveling upstream meets a raft floating downstream. 45 minutes later, the ship stops. Again, I will draw this sketch. So a motorboat goes upstream, and there is a raft which floats downstream with the velocity of the river. And this is the velocity of the boat with respect to the river. And so a motor ship travels up the stream, meets the raft floating downstream. 45 minutes later, that is T1 is given as 45 minutes. The ship stops at a landing stage. So somewhere there is a landing stage where the motorboat stops. Here. And it's standing for 1 hour. So another time interval T2 is 1 hour. Then the ship travels downstream and overtakes the raft in 1 hour. So another time interval is given. That is T3 is the time interval needed for the boat to travel downstream and to overtake the raft, which has gone downstream by some distance. The speed of the ship relative to the, I don't like the word ship, I would say vessel or something like motorboat. Well, anyway, it says the ship relative to the water is constant and equal to v1. So the velocity v1 is given as 10 kilometers per second, 10 kilometers per hour, certainly. Determine the river current velocity v1, v2, the river current velocity v2. No, I denoted the river current velocity as u, so I'm using my own notation here. So how can we solve this problem using geometrical sketch, figure, a geometrical picture? First of all, we have to determine coordinates of moving bodies along the river. And we have to choose the direction, the positive direction, x. So any displacement to the right along this axis will be positive, and displacements in opposite direction, that is up the river stream, will be negative. And then, as these events develop in time, I will have to draw a graph of x versus time. First of all, let's consider the raft. At some initial moment of time, the motorboat met the raft at this point. Let this point where they met first be the beginning or the origin from where all the distances are calculated. So that will be zero marker, zero position along the river. So that will be the initial point in space and time where they met. And the raft goes downstream, that is, along the positive direction of this x-axis. The raft goes downstream at the velocity of the river flow. So the raft goes from this point. The coordinates of the raft must be shown along vertical axis x. As the time goes on, the raft goes to the positive direction of x-axis. So that will be the line showing the change of raft coordinates in time. So the position of the raft, x, the coordinate of the raft, will be given as the velocity of the raft, or the speed of the raft, which is the speed of the river flow, multiplied by time. The larger the time, the larger will be the displacement in the positive direction of axis x. So this is the function x as a function of time, showing the coordinate or the position of the raft. How does it change with time? Now, what happens to the boat? The boat was running in the opposite direction, in the direction of negative values of x. And at the initial time moment, when time was 0, the boat ran near the raft. They met at this point. The boat and the raft met at this point. And so the boat was going in the opposite direction. As the time goes on, the boat coordinate goes to negative values, because the displacement of the boat from this point will be negative. The positive displacements are to the right, and negative displacements are to the left. And the velocity of the boat, in this case, was v1 relative to the water surface. But what about the velocity relative to the ground? That would be v1 minus u, the velocity of the boat minus the velocity of the river flow, because the boat runs, in this particular case, the boat goes up the river stream, so against the flow of the river. So this line is expressed by a formula: the coordinate of the boat equals the velocity of the boat, which is v minus u times t. That's the equation. That's the equation characterizing this line, this straight line, the uniform motion of the boat against the river stream. Then, at some particular time, in 45 minutes, that's indicated here, time moment t1, that is 45 minutes, the boat stopped. And so its coordinate remained constant. Its coordinate remained constant. As time goes on, the boat coordinate remained constant. That is, the line showing the motion of the boat will be horizontal, parallel to the time axis. Time goes on, and the boat coordinate remains constant. The boat is standing. It still is at rest during time interval t2. So that will be time interval t2. And then the boat started downstream to chase the raft. The boat started downstream. That is, from here, the boat went in the positive direction towards the positive directions of x-axis. So the coordinate of the boat increased from negative to positive values, and that can be shown in the graph in this way. And this line is described as this line. I will show the velocity of this line. You know that in this particular axis, when vertical axis describes the coordinate of material point and horizontal axis describes the time, then in this particular graph, the tangent of this angle is the material point velocity. And the velocity when the boat goes downstream is v plus u. So, at this point, the boat overtook the raft. They met again, and we know the time moment. We know when it happened. In time interval t3, 1 hour after the boat started its motion backward. After the boat started its motion, it took the boat time interval t3 to overtake the raft. So what happens in this problem? All the processes can be shown graphically, can be shown on the picture. This is not the graph. This picture does not include any graphs of functions. This is just a sketch indicating what's going on. That there is a river, there is a raft going downstream, and there is a boat going upstream. Well, this is just a sketch showing all the processes that take place in this problem. But there are no graphs of functions here. Such a sketch may be considered as the first step in solution, in solving the problem. The first step. After we have drawn such a simple sketch, it's very often useful. It's useful to go to a more detailed picture, which is presented by functions and graphs of functions. And what kind of functions are here? Coordinates of raft and coordinates of motorboat as functions of time. So here we have a more detailed information about the motion of the raft and the boat and the motorboat. But is it convenient to use such graphs of functions in order to find the unknown quantity, the river flow velocity? Is it convenient to use such a picture? No, it turns out to be not quite convenient. It turns out to be not very useful. When you look at this picture, you have all the information about what's going on at any time moment. When was the raft at this time moment? The raft was here. And when was the boat? The boat was here at this particular coordinate. But it's not very convenient to use such a graphical representation to solve this problem. It may be more convenient if we change the reference frame. If we go to a reference frame connected with some other object. All the graphs here are given provided the reference frame is associated with the river banks, with the ground. Because this is the river flow with respect to the ground, and this is the velocity of the motorboat, again with respect to the ground when we add velocities, and or subtract one velocity from another if the boat goes upstream, or when we add velocities when the boat goes outstream. So all the velocities, everything is shown here with respect to the ground. It may be easier to solve the problem if we consider all the processes from the point of view of people which are on the raft. Somebody is there on the raft, and he can see what's going on around him. And so we can draw similar graphs of functions using the reference frame associated with the raft. Okay, let's do it. Let's do it. And I will use this part of the boat, of the blackboard, this part, in order to draw another picture. So again, this is the vertical axis showing coordinates, but these will be different coordinates, not the same coordinates as in previous case. So I will have to denote the new coordinates somehow differently. Let it be x prime. That is the coordinates of everything, of every object, with respect to the raft. So the new coordinates are measured by people who are sitting here on the raft. And the time, again, the time is the same. In classical physics, the time does not depend on the reference frame. In classical physics, the time is the same here and the same here, because we believe all the clocks show the same time, which is actually not true. In relativistic physics, the time depends on the reference frame, on the observer. Different observers will see different time. So, but in classical physics, the time is the same. What will see those people who sit on the raft? They will see that the raft is at rest. The raft coordinates remain the same always. And what will be the raft coordinates? Well, for these people, probably this coordinate. The initial coordinate is 0, and it remains 0 all the time. So I will show this line shows the motion of the raft with respect to the raft. With respect to the raft coordinates remain unchanged in time, the same. The time goes on and the raft remains here. We are sitting on the raft, and we see that the raft is at rest. It doesn't move with respect to the people who are there on the raft. So that will be the line showing the raft motion. And what will be the line showing the motorboat motion? At this particular moment of time, they met together, the motorboat and the raft were close to one another at this particular moment in time. And the raft and the motorboat was going up the river stream, and the people here on the raft will see that the boat goes to the negative direction of x-axis. If positive direction is chosen to be in the direction of river flow, then the motorboat goes in opposite direction. So the motorboat will go here, and then the motorboat will be standing with respect to the ground. It will be at rest with respect to the ground for an hour, but it will not be at rest with respect to the raft. The motorboat will somehow move in such a way that the distance between the raft and the motorboat will increase in time, and the distance will change at the velocity of the river flow. So the motorboat, after stopping, the motorboat with respect to the raft will continue its motion in such a way that the distance between the raft and the motorboat will increase. And then the motorboat will start to get closer to the raft, and then it will overtake the raft here. And the time intervals are obvious. The first process took t1, the second process, while the boat was at rest with respect to the ground, it took t2 time interval, and that was the time interval t3. What's the difference between this picture and the previous one? The difference is very obvious. In the previous picture, the velocity of the motorboat was different in two cases, when the motorboat went up the stream and when the motorboat went downstream. The velocities were different. When the boat went up the stream, the velocity with respect to the ground was v minus u. And when the boat went upstream, the velocity was v plus u. And that each velocity can be measured as the tangent of this angle, here and here. When we measure everything and the velocities with respect to the raft, it means that we measure the velocity of the motorboat with respect to the water surface. And that is constant. That does not depend on the direction of motion. In whatever direction the boat moves, its velocity with respect to the water surface is the same. So in this picture, that angle beta should equal, I don't need this line, should equal this angle beta. And in this particular case, these are different angles, alpha 1 and alpha 2. And here, this angle represents the velocity or the speed of the boat, and here this angle again is the speed of the boat with respect to the water surface, and the boat moves at the same velocity with respect to the water surface, irrespective of what is the direction of its velocity, up the stream or downstream. With respect to the water, the velocity of the boat is the same. So that's another way to represent all the processes in this going on in this problem using graphs of functions, using the graphs representing the coordinate of each object versus time. And we have two objects, the raft and the motorboat. The raft coordinate is depicted by this line, and the motorboat coordinates are shown by this line, by this graph. And where is the river flow velocity here? That's it. The river flow velocity will be the tangent of this angle. So the tangent of this angle, let it be phi will be equal to the velocity of the river flow. Why this angle? Why this section of the graph represents the river flow velocity? Because during time interval t2, the raft was going downstream by the river flow, and the motorboat was standing still at the river bank. So the velocity of the raft with respect to the boat was equal to the velocity of river flow, and the velocity of the boat with respect to the raft was equal the same. It was the same, but the same with opposite sign. If we are careful about signs, then the sign, and if the sign of this speed here is positive, then the sign of this speed here shall be negative, because the distance is because the tangent of this angle is negative, and the motorboat goes in different direction. So this direction will produce positive velocity, and this direction will produce negative velocity. When the displacement of the motorboat is negative on the first section, and on the second section the velocity is negative. When the displacement of the motorboat is positive, that is, its coordinate is increasing, then its velocity is positive. So strictly speaking, this tangent equals minus u, minus the velocity of the boat. So I have discussed possible graphical representation of all the processes in this problem that take place in this problem. Now we come close to the end of this lecture, so I would ask you to consider this graph and think how this graph can be used to solve the problem. That is, how this graph can be used to find the unknown quantity u, the unknown quantity of the river flow speed. So please think about it at home. It's not a complicated problem. It's easy to use this graph to find the river flow speed. And it's easier to use this graph than the previous one. It's much easier. It will immediately give you the answer. While in this representation, using this frame of reference associated with the ground, it's more difficult to find the solution. While in this reference frame associated with the raft, it's easier to find the solution to this problem. Okay, so upon discussing all these things, I can remind you that we have just discussed the uniform motion, the motion with constant velocity. And the formula is very simple. But a lot of complicated situations may occur based on this simple formula. And a lot of such graphs may be used in order to solve problems involving uniform motion. I just wanted you to understand how to draw such graphs, how to draw such functions, and how to represent graphically all the processes that take place in different problems. Next time we will continue with more complicated cases of kinematics, more complicated issues in kinematics, and also we will consider dynamics. We will start classical Newtonian mechanics. Okay, thank you, and let's finish this lecture in this moment.